In this clip, we're going to revisit the example from 14.7.8, where we have to construct a bin which is meant to minimize surface area and thereby minimize the amount of material needed to build the box. So the surface area function is xy plus 2 xz plus 2 yz, and this is going to be subject to the constraint that the volume is 4. Okay, so let's see. So using Lagrange multipliers, I'm going to work out the gradient. So the gradient of s, let's see, taking the x derivative, I've got y plus 2z in the first coordinate, and then x plus 2z in the second coordinate, and then 2x plus 2y in the third. And then this is supposed to be equal to some constant times, and now I do the partials of v, so I have yz, and then xz, and then xy. Okay, so then this gives me some system of equations. So I've got from the top, y plus 2z equals lambda yz, and x plus 2z equals lambda xz, and then 2x plus 2y equals lambda xy. And then of course we've got the constraint equation, x, y, z equals 4. So that's the system of equations that I have to work with. So notice that now we have 4 equations instead of 3 like we had before when we were back in 14.7.8. But they are simpler equations and hopefully easier to solve. So let's see. So from the first equation, I can, well, here, in general, it's a handy technique to solve all of your equations for one variable and then eliminate it. And since we don't actually need the value of lambda, it's often nice to eliminate lambda. So I'm going to rewrite this as lambda equals y plus 2z over yz. And then similarly from the second equation, I can solve as y equals x plus 2z over xz. And from the third equation, I can get 2x plus 2y over xy. And by splitting apart each of these fractions, so in other words, this looks like y over yz plus 2z over yz, then I can cancel in each case and get something simpler. So 1 over z plus 2 over y. And for this one, I will get 1 over z plus 2 over x. And from this one, I will get 2 over y plus 2 over x. And then I know that all of these are supposed to be equal to each other, since all of them are equal to lambda. And I want to pause just for a second to say that this step here in general is wrong. And the reason why is because I am dividing by y and z and x and z. Those numbers could be 0, right? There's nothing to say that your function might not have a critical point when x is equal to 0 or when y is equal to 0 or when z is equal to 0, in which case this entire step would be complete and utter garbage, meaning that you would lose a whole bunch of solutions. So why is it okay to do it here? Well, the answer is because we can rule out x or y or z being equal to 0. There's two reasons to do that, like we talked about before. One is that they would not satisfy the constraint. Another one is that we want an actual bin, and having a bin with side lengths of 0 is going to be nonsense. So we can effectively rule that out. I just wanted to make a point that when you're messing with the algebra, it's easy to do things that can cause a problem if you're not paying attention. So maybe I'll just make a little side note here that says we can assume that x, y, and z are not equal to 0 for this step. Okay. If you're working on a problem where you can't actually make that assumption, then what you should do is you should treat that as a case. I'll talk about it later. Once you've treated that case, then you can rule it out. So anyways, bringing this back to what's equal to each other, we have, say, 1 over z plus 2 over y equals 1 over z plus 2 over x by combining this and setting them equal to each other, right? So I can subtract the 1 over z from both sides, and we get that x is equal to y. Then I can also use the fact that, let's see, this equation and this equation are equal. And so looking at that equality, I have 1 plus z plus 2 over x equals 2 over y plus 2 over x, and cancel those guys, and I see that y is equal to 2 times z. Okay, so now we can go back to the constraint equation, which we still have not used yet. And so x, y, z equals 4. But we've seen that x is equal to 2z and y is equal to 2z because they're equal to each other, and y is equal to 2z. So the equation looks like this. And then canceling the 4 from each side, I get z cubed equals 1, so z equals 1. And then I can tell that x has to be twice that and y has to be twice that. So my solution is 2, 2, 1, recovered just like it, and matching exactly what we found last time.